local government organization created by the California Public Utilities Commission that provides resources and assistance to homeowners, businesses, and public agencies planning energy efficiency upgrades serving the Southern California region. These services include community education and outreach such as these webinars, rebate and incentive offerings, attractive financing terms, and tools to help identify contractors that have been trained in energy efficiency. Additional resources help homeowners take the next steps towards saving energy. The Energy Network has a great program for multifamily property owners, and we'll tell you a little bit more about this at the end of the webinar. Today's presenter is Graham Irwin. Graham is the principal of Essential Habitat, a Northern California-based design and consulting firm focused on healthy, high-performance, sustainable buildings built to the Passive House standard. Graham was one of the first people in the United States trained in Passive House techniques and studied at the Passive House Institute in Germany as a project certifier. His firm has worked on numerous single-family, multifamily, and commercial Passive House projects throughout California and the U.S. He is certified as a Passive House consultant and designer by the Passive House Institute US, PHI-US, and the Passive House Institute, and is a Build a Green certified green building professional and a USGBC LEED AP. Graham is actively involved in advocacy, promotion, and education. In addition to project-based work, he advises government agencies on energy policy. He has presented at the International and North American Passive House Conferences, West Coast Green, numerous green building professionals guilds, and the Affordable Comfort Institute's Home Performance Conference and JLC Live. He has worked as a trainer for the Passive House Institute US and for the Pacific Gas and Electric Company. Please join me in welcoming Graham. Go ahead, Graham. I apologize, everyone. It looks like we are getting trouble hooking up Graham. Please hold on for 1 minute.
Jack, hello?
Go
hello?
ahead, Graham.
Is that working now?
Yes.
Oh, sorry, must have been the bad connection. In any case, thank you everyone for joining. I apologize for that technical difficulty. Today we're going to talk about Passive House with a focus on Passive House in California, how Passive House relates with renewable energy, and particularly Passive House multifamily projects. This is the agenda. We're going to start with an introduction to Passive House for those of you who don't know what it is, and we'll keep that brief for those of you who do. Then move on to discuss Passive House and renewable energy, how Passive House works in the state of California, and how Passive House compares to California code. And then we'll look at multifamily Passive House and talk a little bit about construction cost, and then have time for questions and answers. It's quite a bit of material to cover, so I will go through it at a reasonable speed and address questions and answers at the end. So why does this even matter? If we look at carbon dioxide emissions by country, we find that California, if it were a country on its own, comes in just a little bit under France, with about 1% of the total emissions in the world per year. And we're about 2 times per capita the average CO2 emissions. There's an old saying that so California goes, so goes the nation. I think also with our general focus on energy efficiency and sustainability in California, we have a real opportunity to lead the country in this approach to efficient buildings. What is Passive House? It's a rigorous voluntary building energy standard, and it was developed or formalized by European scientists around 1990. It was based on super-insulated, passive solar, and low-energy buildings. All of that stuff really got its start in the U.S. in the 1970s after the first oil crisis. U.S. attention sort of fell off of that in the 80s. In Europe, they kind of picked up on that and kept working on it and added some technology and improved computational tools and formalized Passive House about 1990. There are about 25,000 or more buildings, Passive House buildings in the world. The term Passive House is a translation from German, and the German word house, I don't have a great German accent, actually means building. So even though we're seeing Passive House, it's important to keep in mind that this is not just single-family residential. This was the first Passive House in the world was built in Darmstadt, Germany. It's a 4-unit townhouse that the inventor of Passive House lives in and still lives in. He and his family live in the unit on the left here. This was the first Passive House in the U.S., built in 2003 by Katrin Klingenberg, who's the executive director of Passive House Institute U.S. That's in Illinois, a few hours south of Chicago. This was the first Passive House in California, and actually the architect who developed this had been living in Austria, where there's a lot of Passive House. He came back to California and retrofitted his Victorian Berkeley bungalow to Passive House, and I went to a presentation of his in early 2008, and that was how I found out about Passive House, or was first exposed. In 2010, this was the first project I got completed, and this was the first certified Passive House in California, also the first certified retrofit of a Passive House in the United States. And this is a single-family house in Sonoma, built in 1960 originally. How does Passive House work? Basically, the ventilation system is the main mechanical system, and you figure out how much fresh air the occupants need to have a healthy air supply, and then design the building around that. So the heating and cooling loads are adjusted basically to the fresh air supply rather than vice versa. And how it works, you minimize losses and maximize gains with super insulation, high performance windows, air tightness, optimized solar gains, heat recovery ventilation, and efficient equipment, appliances, and lighting. And this is a schematic diagram. The details of this vary with climate. But this is an example from Germany, and again, it's showing a fresh air supply. In this case, it's being taken through the ground to kind of temper the air, but there's a heat recovery ventilation system in here supplying fresh air to the bedrooms and living spaces and pulling exhaust air out of kitchens and bathrooms. And this system is running all the time except when it's nice outside and you open the windows. A key thing is that the warm air that's being pulled out of the building is used to warm the air that's coming in. So the air isn't mixing in this heat recovery ventilator, but it's exchanging the temperature. So we get a constant turnover of fresh air, but we maintain the heat or cool inside the building. So as I kind of hinted, Passive house represents a paradigm shift in terms of building design. Typical building, you design the building and then you do calculations to figure out how much heating and cooling it needs. And then you size the equipment to the building that you have. And I put HVAC, which stands for heating, ventilation, air conditioning, with a lowercase v. Particularly in residential construction, we pay much less attention to ventilation than we do to heating and air conditioning. By contrast, in passive house, we have H capital VAC, so ventilation's the first concern. As I mentioned, we size the ventilation system to provide a good supply of fresh air and then design the shell around that air supply stream. So it's a flip-flop on the original, this previous design methodology. And I put a hair dryer here because that's kind of a tagline of passive house. Often heat your house with a hair dryer, and in many cases that's actually possible. The size of the auxiliary heating system is about the size of a hair dryer when you're done with all passive solar gains and heat from inside and so forth. Passive house goal is basically invest in the shell and minimize the mechanical systems. This is an idealized thing called a compact unit or a magic box, and this is a picture of an example. In Europe, it's about the size of a small refrigerator, and that device contains the water heater, the ventilation system, and the heating and cooling system, and also controls for solar thermal, all in that box. So you basically build your passive house, connect this thing up and plug it in, and that's the deal. This is still an uncommon thing in the United States, and they're still quite expensive because it's sort of a supply and demand thing. But I think in the future, we're going to see buildings with simplified and smaller mechanical systems, not only for cost reasons, but as we move to a renewable energy grid, we're going to have to be a lot more efficient with the energy that we do use. When we talk about a certified passive house, we mean a passive house that meets the passive house standard. It's basically, there's some revisions going on with this in the US and somewhat in Europe as well, but the kind of classic and simplified passive house standard has three aspects to it. There's a blower door test with a maximum air leakage of 0.6 ACH 50. For those of you who know what that is, that would be roughly 10 times tighter than an average California house, I would say. Then there's a maximum heating or cooling demand, which is a measure of the amount of energy that must be added or removed over the course of the year to keep the building comfortable. This can also be met with the maximum heating load, and this is the peak power, so the kind of worst case day, the biggest, the size of the heating system basically. And the third criterion, passive house, is maximum primary energy demand, and that's the primary or source energy required for the building for everything in it: heating, cooling, ventilation, lights, appliances, plug loads, all of those things. And that is before any photovoltaics are added. So the passive house standard is focused on efficiency, low consumption. It doesn't mean that it doesn't recognize the benefit of renewable energy, but it doesn't use renewable energy in the place of efficiency. The first criteria, the air leakage, is measured. The second two criteria are modeled with an energy modeling package such as the Passive House Planning Package, or PHPP. The first two criteria measure the shell efficiency, and the third measures source energy. Again, you'll get these slides at the end, so I wouldn't focus too much on the numbers right now. There won't be a test. Why should we be concerned with source energy? Why is Passive House concerned with source energy? If we look at natural gas being supplied to a homeowner versus electricity, or to a residence or whatever building it is, if you look at natural gas, you'll start out with about 100 units of source energy extracted, there are losses, and by the time it gets to the customer, you've lost about 10%. So for 100 units of natural gas energy, whatever unit it is, extracted, about 90% gets to the end user. By contrast, with electricity, 100 units of source energy, there are losses in processing and transportation, but a huge amount of loss in generation, and then some more in distribution, like in natural gas. But by the time you get to the consumer, you have about a third of the overall energy that you started with. So it's very important to think about source energy more than site energy, because the fuel that you choose has a very big impact on the environmental impact of the building's operation. Source energy varies by grid around the United States, and we won't go too deep into this, but basically these are the breakdown of all the grids around the United States, and it shows various mixtures of hydro, nuclear, natural gas, etc. You'll see this will kind of key in with the next slide. In the Pacific grid, we have a lot of natural gas and hydro and very little coal. This slide is another interesting illustration of this, and it's basically showing the equivalent mile per gallon, the mileage in terms of environmental impact of an electric car. So you can see in the Pacific, which is a relatively cleaner grid, an electric car is the equivalent of a 79 mile per gallon gasoline vehicle. In the middle of the country, where it's mostly coal, it's 33 miles per gallon. So the source energy, the grid conversion factor has a big impact on the environmental impact of using electricity as well. So to kind of sum that up, if we were just looking at site energy, say at these two hypothetical buildings, one powered by all electricity, the other powered by natural gas, and let's say that they use the same amount of site energy, meaning the meters read the same. When you convert to source energy, the all-electric house is using about 3 times that much energy, and the natural gas house about 1.1%. Or I'm sorry, 110%, 1.1 times the energy. And it's not to say that electricity is a poor choice. It's just to say that you need to factor source energy into your calculations. Don't just think about what's read at the meter. Passive house, again, much of the discussion of it and the focus of it is on heating, but as it turns out, passive house buildings are also very effective in controlling cooling. There was a study, this was a study done by the German Passive House Institute on passive houses in Mediterranean climates, similar to much of California. They looked at, this is a graph of cooling load in Seville, Spain, which has a climate similar to Los Angeles. And this is showing a standard or regular construction building. By contrast, this is what happens with a passive house. I'm going to go back one time, just point out that not only does the total amount of cooling get reduced by a lot, but all of these peaks, this is a big problem in California, we'll talk a little bit more about later, all of the peak cooling demand is also clipped. So this reduces overall energy use, but it also has a lot of benefit for peak demand in both heating and cooling. A big piece of passive house benefit in terms of cooling reduction, is night ventilation cooling. This is a graph, generalized graph of parts of the United States where you can do night cooling. Basically means flushing the building out with cool air at night in preparation for hot days. And as you know, in much of California, even in the summertime when it's hot in the daytime, it cools off at night. Having an efficient building shell like a passive house lets that cool air stay cool through much more of the day than with a standard house, where it's immediately getting a lot of heat through low insulation levels and also getting heat through unshaded windows, etc. In terms of performance, the estimates of passive house performance are up to 90% space conditioning savings and 80% total energy reduction before photovoltaics. This is a house that we worked on in Santa Cruz, a 1922 Craftsman that was retrofitted to Passive House. The clients have a great blog if you want to check it out. And the numbers, this is gas and electricity all converted and added on site energy to the same units. But before the house was retrofitted, it was using about 22,000 kilowatt hours per year. Now it's using about 4,300, which is an 80% reduction. A typical California home uses about 20,000, so that's about 22% of a typical home's energy use, and 80% from before the remodel. Here, this is looking at by month before and after. And here's a picture of their energy use, of sort of PG&E, their utility bill showing how their house, which is the blue line, compares to typical houses in the area, as well as what they call efficient similar homes. I think it's important to point out in this that the term efficient doesn't necessarily mean that the building is efficient, but it means that the utility bills are low. So it could be a very inefficient home with very few appliances used, and as you know, a lot of people in Southern California particularly don't heat, I think in Santa Cruz as well, don't use a lot of heat even when it's kind of cold. You know, it's not cold enough that it's a threat to survival, so a lot of people kind of grit their teeth through cold weather. So this green line doesn't mean the building is efficient, but it's the lower utility bills in the area. Likewise, here's a picture of natural gas use. And this one, the fact that Midori House is down here below the efficient similar homes is a very, very hard thing to do in a milder climate like Santa Cruz, because again, a lot of these buildings may be very, you know, they might be the same as the Midori House before it was retrofitted, and people are just not running their heat very much at all. This house, by contrast, stays comfortable all winter and summer. So they're not suffering to achieve this high performance. Passive House benefits also include comfort. So when you have a well-insulated shell with balanced solar gains, you don't find that you're not suffering from radiant cooling in winter. So we talk about radiant heated floors and how good they feel. Many people in inefficient houses, including my own, unfortunately, we have in wintertime radiant cooled floors and walls and ceilings and windows, like this fellow over here, kind of huddling by a fire, trying to reduce the discomfort brought by not only, you know, the air inside these two buildings may be the same temperature, but because the walls and all the interior surfaces are cold, the person is actually radiating heat from their body to those things. In a passive house, much more even and comfortable temperatures. Another big passive house benefit is indoor air quality. Passive house uses mechanical ventilation, and there's a lot of, sometimes find some resistance to the thought of using mechanical ventilation versus natural ventilation. And, you know, I kind of use these two images to conjure up maybe what those things bring to mind psychologically. I would argue that the choice is probably better phrased as controlled ventilation versus random ventilation. Again, this is a centralized heat recovery system in a passive house. Here's the heat recovery ventilator bringing fresh air in from, you know, and they're typically filtered, and you find a good location to get that. It goes through the heat recovery ventilator and it's delivered to the living spaces. And at the same time, the bathrooms and kitchens and laundry areas are having their air extracted, sent through the heat recovery ventilator, where it doesn't mix with the fresh air coming in, but warms it, and that gets sent out of the building. And this is running all the time. Again, unless the weather's nice and you have the windows open, this is giving you a reliable and consistent source of fresh air 24/7. By contrast, in a typical building, this is a chart that shows various sources of leakage. and this would be where the air is being supplied and how it's escaping. So here you have basically a lot of warm air in the wintertime escaping through the ceiling, and that is sucking cold air in through all manner of cracks and leaks in the building. So I call that random ventilation because it occurs at random times, from random locations, in random quantity, at random temperature, of random quality. Again, some of this is coming from some pretty unsavory locations. And this whole system, if you want to call it a system, is mostly either over-ventilating or under-ventilating. There may be a few days a year where it's giving you exactly what you need, but it's simply coincidence. It has nothing to do with how many people are in the building or what's going on in there. It's just more about whether there's wind blowing and whether it's cold or hot outside. Controlled ventilation, by contrast, gives you a constant supply from an optimal location, controlled quantity, comfortable temperature, and a filtered, clean source. And in passive house, the heat recovery ventilation systems we use typically have very high heat recovery efficiency on the order of 80 to 90%, and also very low electrical use. So even though these machines are running all the time, they recycle 8 to 15 times the amount of energy it takes to run them in terms of the heat that they retain in the building. There's a study done in Washington State on typical, these not passive house buildings, but they did a study to figure out where the air in the building was coming from, when you were relying on leaks to get fresh air. And they found that up to 40% of the air in the test houses was coming from the crawl space. Again, I showed how hot, warm air in the winter is going out through the roof and pulling air in from underneath. In houses with crawl spaces, a lot of that's coming from in the crawl space. And anyone that's spent time in the crawl space can well imagine that's not an ideal source of fresh air for your house. Also, passive house benefit is durability. This was a study done in Canada over a heating season, and it looked at how much moisture would get into a wall through a 4x8 sheet of gypsum board. And over the course of a winter, with no leaks in it, about 1/3 of a quart of water. Same sheet of gypsum board with a 1-inch square hole, very small hole, 30 quarts of water. So basically what that means is air leakage is the biggest enemy, aside from failures in the bulk water management on the outside, like leaks in the roof and leaks in flashing. Air leakage from the inside into the building assemblies is the biggest problem in terms of durability. And you're seeing right here, even with a 1-inch square hole, a 90-to-1 ratio in terms of how much water is getting into the walls. And in terms of health, again, you're looking at water getting into building components. If there's too much there, it basically means mold, and these are pictures showing water damage and mold in buildings. Passive house approach uses accurate energy modeling. This is a snapshot from the passive house planning package. There's also a program called Woofy Passive that does a similar function. In both cases, they account for, it's very detailed, it accounts for all of these aspects and more. You can use this to cost optimize the building. This is a front-end, proprietary front-end I've developed that basically looks at all of the building envelope aspects and adjusts them up and down around the design value to figure out which of the measures would be the low-hanging fruit, the easiest ones to improve the building by adjusting. Passive house also relies, as I mentioned earlier, on super insulation. The key principles there are that it's optimized for the climate and the project, and it has no thermal breaks. This is a picture from Germany showing a passive house building here and a non-passive house building behind it. And this is thermal imagery. So the darker colors are colder, reds and purples are warmer, and you can, if you see here the passive house windows, this is in winter, passive house windows are the same temperature as the walls of the non-passive house building, and the windows are very, very hot. So there's a lot of heat being given off by this building compared to this. This one is looking at a diagram showing, basically illustrating thermal breaks. So if you build a typical wall with the studs or the framing going all the way through the wall, the wood carries heat much better than the insulation, and so you get all of these thermal bridges, kind of like vertical stripes through the building. We also use high performance windows, and those will typically gain more winter heat than they lose. So we call the windows in a passive house part of the heating system. They're going to be high performance glazing tuned to the project and location. Again, not every climate needs triple glazed windows. We'll look a little bit at that in a little while when we talk about some studies around California. Thermally broken frames with good seals and hardware. So again, if you're going to use good glazing, like this triple pane glazing that's very efficient, and you put it in an aluminum frame, the heat will come up to the glass and say, oh, well, that looks kind of tough for me. I'm not going to go that way. I'll just take this really easy path through the aluminum and out. So to have a high performance window, you also want a frame that is thermally broken. And this is looking at a wooden frame with some insulation material in there, positioned to reduce the heat flow. And we also, likewise, between the window panes at the edge, you need a spacer to hold the panes apart and also to hold the gas. Usually high performance windows have a gas like argon as opposed to air between the panes. So these spacers need to hold the panes apart and keep the gas in, and a common material again for that is aluminum. So you can end up with the glass being very efficient, but the heat looks at the spacer that's made of aluminum and says, hey, we don't have to worry about that. We'll zip right through there. So these so-called super spacers are they have a better R value, much better R value in terms of a spacer than aluminum. Passive house approach, also optimizing solar gains. And this is not to say that all passive, I want to draw a bit of a difference between passive solar and passive house. It's not to say that all passive solar projects are problematic. Some of them worked really well, but there were problems with a lot of them. This again was the idea that one could use the sun to warm your home directly, and if some of that is good, then more has to be better. So it ended up with a lot of buildings, often in the 70s, that were heavily glazed, an awful lot of south glazing, and the building would overheat in the daytime. Even in the winter, often there would be a lot of glare, and it would bleach furnishings and carpets and rugs and all that kind of stuff. And then often this was single pane glass, so at night all the heat would flow back out again. So then they'd often turn to thermal mass walls and water tubes and all this other kind of stuff to kind of hold that heat in the building through the night. By contrast, passive house does use passive solar gains, but it's combined with a very efficient building shell, so the amount of solar gains are far less required to meet the heating demand. And the shading is also important, so we balance heating and cooling. You get consistent comfort and performance, and you have a lot more flexibility. These are all examples of passive houses, and you can see that these are single family, but a wide variety of architectural styles possible with passive house, because again, it utilizes solar gains where beneficial, but it's not tied to that and not overly dependent on that. And passive house approach also relies on air tightness and ventilation, and we talked about this previously. Heat recovery, pulling warm, moist air out of bathrooms, kitchens, laundries, taking it out of the building, bringing fresh air in and delivering it to bedrooms and living spaces. And that's basically the idea. And again, in fair weather, the windows open, just like in any other house. Just that when the weather isn't nice, you can close the windows and get them sealed and run your heat recovery ventilation and keep the heat inside or keep the heat outside in summer. This is looking at a heat recovery ventilator. Again, Stale air being drawn in from kitchens and bathrooms goes through the heater core and gets sent to the outside. Fresh air drawn in through the heat exchange core, and the heat from the exhaust air goes to the supply air, though the air streams don't mix, and then that gets delivered to the house. And this is doing 80 to 90% heat recovery. Here's a thermal image of an actual machine running. And this is just looking at summer versus winter. So if it's summertime and it's 88 outside and it's 74 inside, the air that you would be bringing in would be warmer than the air leaving. So the air leaving will actually cool the air that's coming in. And conversely, in winter, if it's colder outside than inside, the air that's being taken out of the house is used to warm the air coming in. So it maintains the interior temperature, and with an ERV, or enthalpy recovery ventilator, it can also maintain the interior moisture in a very humid climate or an extremely dry climate. Those are a good idea. I'm going to talk now about passive house and renewable energy. First, for some context, this is an average California household. So this is all the households that were in this residential appliance saturation survey, which was a survey done with a number of California utilities. So we've got in here new homes, old homes, single family, mobile homes, you know, all over the state, all kind of averaged out. This is looking at site energy, and what we see is that heating and hot water are the two biggest site energy demands across the state. Again, this will vary by building type and location, but this is a general overview of it. If we look at the site energy use, and this would be combining gas and electricity again together into one number, the average is about 16,600 kilowatt hours. If I divide that by 1,500 kilowatt hours per kilowatt of rated PV, which is an optimistic but reasonable estimate of what a PV system can produce, you would need about 11 kilowatts of PV, which would take up about 1,100 square feet to reach net zero site energy, which would mean that the PV system were putting as much energy into the grid over the course of the year as the household is using. And that 1,100 square feet may not seem like a lot in some situations, but if you think about that having to be applied on every household in the state, it's a lot of area. This was an article from the Sacramento Bee from 2009, and they basically said that rooftop solar, if it were rolled out to its, the greatest extent possible, would meet about 2.5% of Sacramento municipal utility district's energy demands. And in the same article, they talked about how much square footage, how much land we would have to cover to meet the U.S. energy demand, and it's about 1.7% of the U.S., or about 53,000 square miles. And it goes on to say it's always cheaper to reduce your energy demand. That's about the size of Arkansas, I think. I looked through these at one point, about the size of the state of Arkansas, and a pretty big chunk of California for that matter. You can also look at California's energy use. Here I use the CEPHEUS statistics. In California, 265,000 gigawatt hours per year of electricity used, 29 to 42% from natural gas, 10 to 20% from hydro, 15 to 30% imported. Natural gas, about 2 trillion cubic feet per year, which is about 20 billion therms per year. About half of that's for electricity generation. So if we do the similar math, 265,000 gigawatt hours, I get 171 gigawatt PV system to cover electricity. And if I assume that half of the natural gas went to electricity, we'll take the other half, and that's about 293,000 gigawatt hours. We get another 195 gigawatts of PV. If we add those together, we get 372 gigawatts. That's billions of watts of PV. It's about 100 square feet per kilowatt of PV, That adds up to 37 billion square feet, or about 1,300 square miles. It's about almost 1% of California's land mass. It would cover the county I live in almost 3 times, likewise Santa Cruz. So this is a lot of PV that we need to meet current energy use. Again, my pitch here is that we need to focus, in addition to renewable energy generation, on using a lot less energy, particularly wasting a lot less energy. I don't think we need to get to the point where we need to suffer, but the waste of energy is something we need to do away with, in my opinion. If we look at the biggest challenge with powering buildings with renewable energy is actually heating them. This is a graph that shows, this is from San Jose, but this is showing heating demand across the course of a year. And this is basically a very fancy way of showing that you need a lot of heating in January and February and November and December, and not very much in July, August, and September. Not much of a shock there. This is called summertime, and it's warm, right? And it's cold in winter. If we look at the available solar energy, we see a rather inconvenient mismatch, and that is there's more solar energy available in the summertime than in winter, and it's not coincidence that there's very little heating required when there's a lot of solar energy required. That's why it is summer. It's summer because there's a lot of sun out. It's winter because there isn't much sun out. It's cold in winter because there's not much sun. So we basically need a lot of heating when there's not much sun. Again, this yellow curve might show renewable energy available, but the red pieces left over at present are coming from basically fossil fuel sources mostly. We can try to increase the amount of renewable energy like this, and as you see, because the curve is inverse to the demand, we end up with certainly more renewable energy, but mostly what we get is a peak in the summer and not much in winter. More efficient to reduce demand like so, to take it down. Even with the same amount of renewable energy, we've gotten rid of it. Another aspect of this is, if you look at internal heat gains, which is all these uses inside the building, if you can harvest those, you can kind of boost your renewable and reused energy up and get to a very small fraction of heating demand left over. I'm running a little bit late, so I'm going to try to pick this up. Looking here, you can see the peak demand is in air conditioning in afternoons. Our solar demand actually comes earlier than that in the day, around noon. Again, fairly obvious given the geometry of the way the sun passes. They're seeing this in Hawaii already and hypothesizing this in California. They call this the Nessie curve because it kind of looks like the Loch Ness Monster. This one, the duck curve, because it kind of looks like a duck. But in Hawaii and Germany, they've already seen conditions where in the middle of the day, they actually have extra power that they can't use. So the price is being driven negative. And that may spell the end of net zero, because net zero relies on the value of electricity when PV produces it the most, which is in the middle of the summer. The problem is when more and more PV is added, everybody's supplying that power at the same time. If we can look at a passive house, by contrast, as a sort of thermal storage battery, this is looking at temperature swings on a daily basis in the wintertime outside, and this is kind of average. If you have a fairly inefficient building, its interior temperature is going to swing up and down pretty much hourly with the outdoor temperature. As you get a more and more efficient building, these are becoming more and more efficient, you get to a certain point, the building hardly notices the swings in a day. It tends to average out to the average temperature, but it isn't needing heat or cooling at the peak demand times. You can kind of heat or cool it at any time of the day, and that could be very beneficial in a renewable energy grid and in a grid with time of use pricing. So these buildings can act as batteries. This is, I'm going to try to keep speeding up. This is just kind of a list of projects that we've worked on, passive house projects in California to date. There are probably 50 total at this point, most of them in and around the Bay Area. So I've been very interested in trying to get this adopted elsewhere in the state. And so I'm doing a study right now looking at passive house versus energy code throughout California, and there are 3 prototype buildings: a single story, single family, 2-story, and a multifamily. And the first part of this study, it's a work in progress, was on the single family building. And this is looking at each of the climate zones, all 16 climate zones, and a set of improvements going from code to passive house on the end here. These jumps are because I've done a raised floor, a code raised floor, and then I switch to slab on grade and then re-optimize it. And slab on grade needs no, code requires no insulation. So we kind of have a very good efficient crawl space house, and then put the code slab in and it goes back up and then we fix it. In any case, this is, without going into too much detail, this is showing kind of the wide variety of heating and cooling demand through code across the state and where we get to with passive house in each of the climate zones. This is looking at climate zones across California, how much reduction was achieved through passive house, how much heating and cooling demand was saved per year, and how many passive house buildings in each climate zone can be heated and cooled with the same amount of energy that a single code house would use. In these milder climate zones, heat recovery ventilation was not necessary up front. I just kind of put it in and said, well, if you chose to use it, what benefit would it give you? Again, this will be available later in detail, but I just kind of wanted to give you a taste of what this looks like. Huge amount of numbers here, but it's just looking at what code looks like compared to passive house. And here, the code numbers are the non-bold numbers. It's bolded wherever things were changed for passive house. And there wasn't a tremendous amount of change. Main thing was air tightness and under slab insulation, and then the other things varied by climate zone. Some places it's already basically code with those 2 things added. Looking at multifamily, so early on when that first passive house was built, it was built as an experiment, and soon after, Amory Levins from the Rocky Mountain Institute met Dr. Feist, who's the guy that built that, and said, this is not an experiment, this is the solution. You need to find a way to make this more cost effective. So fairly soon after that, there was a multi-country effort called CEPHEUS. You can find this on the internet, you can find the whole report, but they built a number of multifamily passive houses and some single family around Europe, built them, monitored them, looked at what could be done to lower costs and where the benefits were, and basically prove the concept. And it did a huge amount. I'm just going to flip through, not really talk about these, but these are the projects that were involved in this study, and all back around 2000. But this is what really gave a lot of momentum to passive house and saw it start getting adopted widely in Europe. Here's a quick look at modeled versus the basic. These are the heating requirements of what these code, if they were built to code, of all of these various projects, and what they were as passive house, and their estimate was 83% savings, which turned out to be fairly close, the modeling versus the outcome. In Europe since then, this is 149 apartments in Frankfurt, 230 they're building this up, a whole neighborhood of passive house through the year 2020. I visited this in Innsbruck. 354 units of affordable housing. See these tubes sticking up here are actually the fresh air intakes for the buildings, and they all go through the ground first to use the ground to kind of warm the air up. So I'm going to start wrapping up soon. This was the first passive house in the U.S., multifamily. Again, just kind of flipping through to give you some context to what's been done so far and what's in the works. This is the largest to date that it's under construction in Oregon. 4-unit condo in San Francisco we're working on right now. So passive house, why is multifamily beneficial compared to single family? Ironically, most of the projects so far in the U.S. have been single family. Multifamily, it's even easier. You get better floor area to surface ratio. The envelope is easier. You've got more people living closer together, so those heat gains work in your benefit. You can save a lot more mechanical equipment. And for people who are building and owning the buildings long term, you get predictable and lower operational costs. This was I'm going to finish up with this quick study. This was a feasibility study for 20 units of affordable housing we did in Whittier. Basically cost optimized this and took these 4 steps to improve the building. This was a feasibility study because it was already basically under construction or in construction drawing phase. 55% heating, 43% cooling savings, and likewise heating load. The building was constructed with 21 gas furnaces. By contrast, the whole thing as a passive house could have been done with 1 small gas furnace. So you can see in multifamily, you can save a lot of equipment up front in addition to the costs of operation. General cost, this is, in the US, I think that's probably true, between 5 and 15% upfront cost. In Europe, and there have been a few in the US and Europe now, they're building these for the same cost as a code-built building upfront and a lifetime of energy savings. If you need more information, these are various links you can follow to get information, and that is the end of the presentation. I apologize for being a little long-winded. I'll answer as many questions as we have time for, and then I can also answer by email. I thank you for your time and attention.
Thank you, Graham. We do seem to have a few questions, and what I'm going to say is, because the webinar will end relatively soon, is please keep sending in your questions. We will definitely answer them in the follow-up email. Graham, actually right now we have one that we might be able to answer. Do you personally have any experience with earth tubes, and how are tube moisture and biological contaminants controlled?
Great question. I have no personal experience with that. My understanding is they use piping that is antimicrobial. I think my preferred approach is what they call a brine loop, where instead of running the earth through the air through the ground, you have PEX tubing in the ground and you pump an antifreeze through the ground and then use a heat exchanger to warm the air. Particularly in a humid environment, you've got to be really careful with earth tubes.
Okay, great. We do have 2 more questions, but I apologize. We'll follow these up. We'll answer them in the follow-up email. I'd just like to say that for multifamily property owners and managers, like some of you guys in our audience, actually, this webinar is being offered 1 CEU for Certified Passive House Consultants. You'll enter in this code, and if you follow this link, you'll be able to submit your CEUs for that. So if you are a Certified Passive House Consultant, please take advantage of this. Graham was actually able to get this connection for us, so we thank you, Graham.
You're welcome. And I will, I apologize for not having much time for questions. I will answer every question that's sent.
Yes, definitely. For multifamily property owners and managers like some of you in our audience, the Energy Network Multifamily Program is a fantastic resource. It provides significant rebates and technical assistance to help you complete energy and water upgrades for your buildings. This program offers rebates for up to $1,200 per unit, which includes upgrades to windows, lighting, HVAC, appliances, water fixtures, and many more. Benefits include lowering your operating costs, increasing your property value, along with improving tenant retention. To learn more, you can visit theenergynetwork.com or call us at 949-264-2062. In addition, this webinar series, the entire Multifamily Sustainable series, is being co-sponsored by Greenpoint Rated, which is the leading green home certification system in California with over 31,000 homes certified, including multifamily properties. The Greenpoint Rated system is a simple, affordable, and flexible rating system used by countless builders and developers. If you guys have additional questions about this, please visit us at builditgreen.org/greenpointrated. Upcoming webinars that we have water conservation in multifamily buildings being presented by Nathan Ho of Eden Housing. That's on May 26th, and you'll be able to register just the same way you registered for this webinar using this link here. In addition, a few days later on the 28th, we're having part 2 of a 3-part series for Cornerstone Concept for Quality Property Management. Again, use this link to register, please. If you have any questions for the Energy Network multifamily program specifically, here's the contact information for David Myers and Jonathan Austin, who are our Southern California Regional Director and our Multifamily Sales and Program Outreach Manager. Lastly, I'd just like to thank Graham again for joining us and offering his expertise on passive house design and technology and operations. It's really informative, and please keep sending us questions. We'll have Graham follow up in an email with any of the answers that we have. And again, we will send out the presentation and the slide deck for you all because I know there's a lot of valuable information in there. Thank you all for joining us. We will see you again next time, and Graham, thank you as well.
Thank you.
All right, everyone, we will see you next time.